Do you see my screen now with my keynote speech?
Yes, sir.
Okay, thank you. And again, as introduced, my name is Mohammed Ubaidat. I am the founding dean for the College of Computing and Informatics at the University of Sharjah. I've been in this position for 1 year and 3 months. Before that, I spent about 30 years in the United States as a professor and an academic leader in various positions. And I obtained my PhD from the Ohio State University, and I served in various professional activities in the worldwide, actually, including the one nationally in the United States. My talk is entitled Biometric-Based Cybersecurity Methodologies for Risk-Based Authentication in Web Systems. And this work is not only due to my efforts, it's due to my many collaborators, including Isaac Wangong, Isa Trau, Balkis Sadoun, and Maher Ali, and others. This slide shows the list of my research area, which includes cybersecurity, biometric-based security, wireless networks, among others, AI and data analytics, etc. This is the journal which I founded in 2018, Security and Privacy, that's published by Wiley, which is a popular journal, and we have 4 key areas there: security and business, healthcare and society, communication security, including cryptography, of course, information security, communication security, and privacy. And privacy has become an important issue in recent days, especially in North Africa and Europe. I've been also editor-in-chief of the International Journal of Communication System by Wiley since 1997, actually. It's amazing. It's like yesterday. This is a book we published recently, Biometric-Based Physical and Cybersecurity Systems by Springer. This is a best-selling book, Security of E-System and Computer Network, published by Cambridge. And as a matter of fact, I have a position also in China. I am the People Republic of China Distinguished Professor at University of Science and Technology. And a few years ago, I taught a PhD class in summer for 5 days, 1 week, basically. And when I tell my students this will be the text, they said, "Oh, this is good, the professor." I said, "Do you like my book?" They said, "Of course we like it, but we like one aspect of your book, that your book is available in Chinese." And until that time, I did not see my book in Chinese. So on the break, they had brought me my book in Chinese. I told them I did not put a single letter in it. Social network, for instance, cybersecurity and machine learning, and smart cities and home. This is a very popular book also by Elsevier. And we have a book, Deep Learning for Industrial Internet of Things Application, that's coming hopefully the next year. Simulation and modeling methodologies and technologies. Internet of Things and personal healthcare, social network, for instance, cybersecurity and machine learning, principle of wireless sensor network. This is a popular text that's being adopted all over the world, and it's co-authored with my friend Sudhi Misra from IIT Kharagpur. Modeling and simulation of computer network and systems, that is also Springer. Handbook of Green Information and Communication Systems, that is Elsevier. Cooperative networking and pervasive computing and networking, Wiley. Wireless network, this is one of the earliest books in wireless network. It was popular then, but we need to update it. Performance evaluation of computer and telecommunication system, that's published by Wiley and used as a textbook all over the world. This is a very popular book as textbook. Optical lens also, we published it back in 2003. So the objective of this talk is that we introduce to you a proposal for a new online risk-based authentication system, which provides more robust user identity information by combining the mouse dynamics or mouse gestures and keystroke dynamics biometrics in multimodal framework. We tried, mouse gestures and keystroke dynamics. These are considered behavior biometrics, because biometrics means physiological one and behavior one. Physiological one, like the fingerprint, like the iris, like the retina, while behavior, like the voice is considered behavior. and keystroke dynamics and mouse gesture. Experimental evaluation of our proposed model with the 24 participants gave us an equal error rate of 8.2%. Equal error rate when the false acceptance rate and false rejection rate are equal. This is, it may not look impressive to you, but for us, it's very promising considering that we are dealing with free text and free mouse movement, and the fact that many web sessions tend to be short. In this context, biometric schemes have progressed to become proven secure user identification system, especially after September 11, 2001. And different from traditional security schemes, they don't require users to hold an identity card, a token, or long password to log into different accounts. We have two main categories for biometrics, physiological and behavior. And as you see in the screen, physiological like the face geometry, fingerprint, the hand geometry, the iris, even DNA, and Udur actually. And one of the leading scientists in the world that doing work on this is a Professor Anil Jain from Michigan State University, who happens to be on the board of trustees of the Mohammed bin Zayed University for AI in the United Arab Emirates. They established a university dedicated to AI. And we have behavior biometrics, including keystroke dynamics, mouse gestures, the regular signature, and voice. How it works, from the human, we extract features that are unique for the individual. Even twins, they don't have the same features for the same model. So you have biomedical devices, you register, you get a template. Of course, involved there need to be sensors like cameras, etc., or scanners. So you have the sensor, which could be a camera or a scanner. You need to have pre-processing to remove noise, then extract features. Then you need to deal with the template generation and matching and others. A biometric system can provide the following two main functions: the verification, which means authenticates its users in conjunction with smart card, username, or ID number. Identification authenticates its user from the biometric characteristics alone without the use of smart card, username, or ID. These are examples on these: facial thermogram, facial features, the iris, which is considered one of the most, actually it's the most accurate biometric scheme, retina, voice, print, and others. If you go to the cost versus accuracy, you will find that iris is the most accurate among all of these, but relatively it is the most expensive. Given today's technology, the cost is not a big deal these days. This is an example where biometric is being used in Walt Disney or Disneyland. You know, people go in, whether in Orlando or in Los Angeles area, go for family before COVID-19 pandemic. They take the family, 5 members of the family, they go, they get pass for everybody. Then after 2 days, they get pass for 1 week. After 2 days, the kids get bored. They want to go back home to play with their friends in the neighborhood. So they say, Bobby, Daddy, we need to go back home. So, but they're passed for 1 week. So in the morning at the breakfast, they meet with the newcomers, you know, and they talk. They said, okay, we are done. Our pass has 3 days more. Take them and you could use them. And some people sell them actually. So they go the next day and they go basically free. So Disney and Walt Disney thought of it. If this happens, then they will run out of business. So what they put in place, you have to be there. You need to have an ID, identification card. But in addition, you need to have a biometric feature to secure that it's you who's using it. It's you who paid the money, you are using it. Okay. So that's an example on that also. Attacks on eBay's system can be divided into active and passive attack. Active attack involve changing data stream or creating false one. And they can be classified into massacred, replay, modification of message, and denial of service. Mass-acquired attack is type of attack in which one system entity illegitimately poses as another. Replay entails the passive gathering of data and its subsequent retransmission, and modification means altering the data. Denial of service is an attempt to make a computer resource unavailable to its intended users, and usually competitors do that, or people who are angry at the company, they want to do damage for the company, especially if that employee or past employee has been fired from the company. Passive attack include, as I said, eavesdropping and snooping on the transmission of data. In this case, the hacker seeks to either learn the content of the message he wants to learn because of nosiness, or because such information, such knowledge help that competitor, for example, or enemy to be prepared or to benefit from the information. Or analyze the traffic. Analyzing the traffic can give you lots of information about the frequency and the habit, etc. And that's important, for example, in national security applications. Major characteristic of a good biometric system include universality. It should be, that means every person should have that metric. For a study for the United States of America, for the Congress, as a matter of fact, the study found out that 2% of the US citizens, they don't have legitimate fingerprints, which means you don't consider fingerprint universal specifically, because 2% are important population in a country that has over 330 million. That's why in such case, they try to have a multimodal or dual. They could have a fingerprint along with iris or with, let us say, voice and so on. Uniqueness, this means no two individuals have the same characteristic, even twins. Permanence, the characteristic doesn't vary in time. Collectability, this means that the characteristic can be quantitatively measured. Practically, biometric collection must be non-disturbing, dependable, which means reliable and robust, and should be rewarding and cost-effective. In terms of keystroke dynamics, long ago, since the start of the 20th century, psychologists and mathematicians have tested and experimented with human actions and behavior. And they were influenced by the era of telegraph operators. And even we're human beings, when you sit with somebody, okay, and you know him, whether a classmate or a colleague at work, after a while you say, oh, okay, this is Arun who just moved, okay? This is Venkata, this is Ali, this is Muhammad, this is Tony, this is John. You start to associate the footsteps and the sound they make with that person. And even during the telegraph operators, when people used to come to the telegraph, because you have basically typewriters, you say, oh, Alice is working today, for example, Lata is working today, and so on. But nowadays, the telegraph key has been replaced by other input peripheral, the keyboard and mouse. And keyboard, they could be hard keyboard or soft keyboard. Me and our groups, we're one of the few people who start working on that early in the 90s and late 80s, actually. We conducted work trying to check the inter-character time interval, and we found that unique for individual. And some people worked in that, but our uniqueness in that work was the whole time, which is called the dwell time. Nobody tried it before us. And the challenge in such situation was to quantitate the data. You measure inter-key times between the typing of, for example, a phrase like my last name, Obidat, O-B-A-I. You measure the time between entering O and B, B and A. And at that time, we use assembly language programming and the trap of the keyboard, And that was, we called it at that time, inter-key times. Now we call it the flight time. And we followed that by hold times, which is the dwell time. And we're the first people to found that hold times, which is now dwell time called, is unique for any individual. There are no two people, they have the same characteristic. And we're able to quantify measuring the data. When we merge both of them, the dwell time and the flight time together, we even get excellent accuracy. In the beginning, for pre-clustering, we use pattern recognition technique, and we get reasonable accuracy, but the false acceptance rate and false rejection rate, they were not zero. When we merge the hold time and flight time together, or hold time and enter key times together, we get 100% accuracy, which means we get zero error. False acceptance rate and false rejection rates, they were zero. And of course, we get even better accuracy when you use a neural network for pre-clustering as compared to traditional pattern recognition technique. This is some of the work we did earlier when we said when we use a neural network, we get a better accuracy than using the pattern recognition for pre-clustering. The data was collected over 8-week period, and we bribed our students, as a matter of fact, at that time. They were the subject, mainly students, especially graduate students, and some colleagues also. We bribed them by bringing them coffee and a donut and chocolate bars, etc. And we tested over 8 weeks, because the idea when you type in a keyboard is one day you are sick, one day you are not in good mood. So over 8 weeks, that period will represent, the usual mood of the person. A computer program was written in assembly language program and gathers the key hit and key release times on desktop PC to the nearest 0.1 millisecond. The system measures the time duration between the moment every key button is hit to the moment it is released. And that's, we call it enter key times. The participant were asked to enter the same phrase, which was not visible during the process of typing. Therefore, it was important to display the message on the monitor after entering it. The time duration between keystroke was then collected by using PC-based data acquisition system, which use assembly language programming because we need things to be fast. And for example, if the password or the phrase is OBDAT, OBAI, we entered, then the assembly language program would compute the time duration between the letters O, B, B, A, and so on. We gave open period of time to the participants, and this helped us in averaging out the effect of uncorrelated sources of noise that could be introduced by instrument and participants. This flowchart summarizes the process. You enter the phrase, then you extract the features, then you apply the classification technique, then you make a decision, yes or no, authorize or not authorize for the user, which means is the user legitimate or not legitimate. When we use at that time a pattern recognition technique like k-means and cosine measure, minimum distance, etc., we found type 1 error and type 2. At that time, everybody was calling false acceptance rate and false rejection rate as type 1 error and type 2 errors. We get a low error rate for base rules and potential function, but actually we did not get zero error. That is for enter key time, which now we call them the flight time. When we use the whole time there, we get same thing, almost the same, but less errors. When we combine the enter key and hold time for pattern recognition, we get even better results. But when we use a neural networks paradigm like linear vector quantization, RBVFN, fuzzy ArcMap, we get in some of these zero error, whether it is false acceptance rate and false rejection rate. For hold times, we even get better. As you see, more than one paradigm provide us with zero. When you combine hold time and enter key times, we get zero for 3 of them, actually more than 3 if you look at it. So now, these days, we have smartphones. Smartphones, they have a soft keyboard, so we have to deal with that. The good news is that most of these operating systems, like Android, they have built-in routines to measure some of these features, whether they are timing and non-timing features. So these features are divided into two main classes for soft key boards: timing features and non-timing features. Timing features can be collected from special timer on mobile device from a hook within the operating system or by event handler, which are picked up when the key is pressed or released. The main two event times are pressing time when you press into the soft key, which is the time stamp when the key is held down, and the releasing time, which is the time stamp when the key is released up. This shows you example on these, the timing feature description. For example, down up, duration of time from a key is pressed until it is released. Some people call it dwell time or hold time. Up, latency from one key is released until the next key is released, and so on. Non-timing features, other features are finger pressure. How much when you type in the soft key, how much pressure you put. The good news, Android and other operating systems for smartphones, they have built-in features to collect such information. Position on the key, the XY coordinates, okay? The size of the surface touched by the finger, which is self-explanatory, how much area is there. All these features may change during the duration of period of a key when pressed or released, and can be a source of multiple values for the same features. For every key pressed, we can extract many features as described in the table below. Pressure is measured of the force applied by the finger on the touch screen. Some of us, they put more pressure, while others, they put less. Position, this value is being described as XY coordinates. The size is the measure of the surface of finger in contact with the key when key down event or key up event are detected. Finger placement, where the finger is placed on the device or keyboard. Finger choice, some of us rely on the index, other relies on the middle finger, the thumb, you know it, you know. Which finger is being used to type, and distance, actual distance between the letter on the key surface. We classify the results based on the features that have been used to assess performance, and all the mentioned studies were executed on touchscreen devices with Android operating system. This shows you performance measure for recent studies using keystroke dynamics. Okay, that, for example, here, the study by reference 5, which is a paper we'll show you later on. Time and pressure, they get equal error rate. Equal error rate, it is the rate when false acceptance rate and false rejection rate are equal, which means each of them is 2.3%. Excuse me. We call that rate in such case equal error rate. The study by the authors in 3, time, pressure, size, and position, they get 2.8%, and so on. That tells you all of these. In our related work, we chose a neural network learning machine, multi-layer perceptron, which is feed-forward neural network that maps sets of input data into set of output. We rely on, again, multi-layer perceptron, which consists of multi-layers of nodes in a network, which has fully connected nodes. Multi-layer perceptron, from now on we'll call it MLP, utilizes the well-known supervised learning technique, the backpropagation algorithm. MLP can be configured using different parameter configuration. Learning rate, which is understood, it's carefully selected to ensure that the weights values converge to a response fast enough without producing instability. Moment rate, the parameter adds a percentage of the already applied weight deviation to each subsequent weight deviation. Number of nodes of neurons in each layer, especially the hidden layer. The MLP, which uses backpropagation algorithm for training and adjusting the weights there, is used. The proposed model was trained and tested using real data set samples, which were collected by the proposed design virtual keyboard. It was installed in a specific Android-based touchscreen device. The table shows you some of these features there. Yeah, this shows you Android system call events, time, get event, get time in milliseconds for each event there, a pressure, etc. Get a pressure level for finger on the touch screen, and so on. In the figure to come here, this shows you how these were interfaced. And the collected data set record consists of timing and non-timing data, as we mentioned earlier. In the case of Android, motion, event, and gesture classes provide functions to collect input data, input time, duration, pressure level, size, and position. In the case of Android, motion, event, and gesture class provide function to collect input data, include input time, duration, pressure level, size, position, and coordinates. This figure shows you the keystroke dynamics methodology, how it will work, which is already explained it in a previous figure. In experiment 1, excuse me, the main goal of this experiment is to evaluate the MLP classifier among multiple classifiers using the same data set as a reference, and we use this data set, Sabich. And this is public data set for Android platforms, number of subjects, in our case 42, 24 males and 18 female. This is the password, number of sessions, devices, which means the phones we use. The features considered, which include keyhole time, down time, up, down time, when you hit and release. Key pressure, finger area, average hold times, and average finger area, and average pressure. Our chosen toolkit for neural network training and testing is Weka, which is famous, and it is a data mining tool developed at University of Waikato in New Zealand. Again, here shows you the experiment setup, experiment requirement, and description. For example, the setting here, learning rate, parameters, and so on. The classifier we considered MLP, SMO, simple logic. We try to compare with other classifier. The table shows you the experiment result there, and if you use MLP, you get correctly classified 85 or incorrectly 14%, which is relatively better than the other competing classifiers. Experiment number 2, here are the number of volunteers and the number of samples collected and so on. This shows you the result, and all of them, MLP is pretty much the best among other possible classifiers we tried. We consider them competitors. This is a comparison of recent research work, including our scheme, reference 4, etc. We showed you that. And our work provided with 0.9% equal error rate, which means false acceptance rate and false rejection rate. They were equal to 0.9%, which is the best compared to the other competing schemes and from these references. And these are the references which I promised to show you when I refer to 5. This is reference 5 for the work. Observation, keystroke dynamics providing valid characteristic with acceptable level in performance measure as a second factor authentication means. So this is the top of what we use. This behavior-based system is the least expensive second factor authentication technique because no additional hardware is required. Timing and non-timing combination, okay. It's timing like the up or up down and so on. Non-timing like the finger area, the pressure. So timing and non-timing combination and analysis of features can improve security level of keystroke dynamics authentication system. We followed this work by doing it for risk-based authentication. So a key characteristic of risk-based authentication is that the process must be virtually invisible to end user, which means the model, in our model, mouse and keystroke dynamics were utilized, must be captured and process freely. Although keystroke dynamics biometric has been studied extensively and used for authentication since the early 80s, most of the existing schemes have focused mainly on fixed text configuration. Fixed text recognition consists of enrolling the user using a predefined text or phrase and performing the detection by asking the user to type exactly the same string. While this may be used in static authentication like logon, it is not appropriate in risk-based authentication where you want, for example, in the middle of the session, you need to block the hacker, where the user must be authenticated in an intrusive way. Under such scenario, the user must be authenticated based on text freely typed, which doesn't necessarily match the enrollment sample. And this is referred to as free text detection. Free text detection in web environment is very challenging and because, of course, we have limited amount of keystroke involved in many web sessions, online banking, for example. Similar challenges are involved in free mouse dynamic biometric analysis. Risk-based authentication, we call it from now on RBA, uses contextual and historical information along with internet communication sessions data to determine the probability of whether or not a user interaction is genuine. This is a legitimate user or not. These are popular in e-commerce and e-government transaction. However, many of the historical and contextual data used in existing RBA systems can be spoofed. As alternative, we propose a more robust RBA system that combines both the mouse and keystroke data captured in online session. The challenge is here, transparent data collection, free mouse and keystroke actions, limited mouse or keystroke dynamics sample size in typical web sessions. These are challenges. So here we extract a separate model of the user behavior for each biometric modality using a Bayesian network. For the keystroke, there is one, and for mouse, there is one, and each of these Bayesian model will be for each user. Combine individual biometric scores using Bayesian fusion scheme, authentication user by authenticating of users by computing and comparing global biometric score against a predefined threshold. For traditional keystroke dynamics, we usually go to dwell time, which is the length of the time you hold down, or call it hold time in the old days, or flight time, which is the enter key times. This shows you what we mean by dwell time or enter key time, when you enter letter A and the other A or B and so on. And this is a dwell time. And this is the flight time, okay, between one key and the other. So this is the whole time when you push on A and release it. This is called dwell time or hold time. The enter key time or fly time is when you push on letter A and then go to B. We call that enter key or fly time between A and B. And the same thing applies to dwell time for the key B and so on. We consider 4 categories of keystrokes based on ASCII code and keyboard layout: uppercase keystrokes, lowercase keystrokes, control keystrokes, and other keystrokes, control keys. We define 20 keystroke features. Example of these include mean of dwell time, represented by M_DT. Mean of a flight time, standard deviation of dwell time, and so on. These give you other also mean flight time and mean of dwell time. This example on these samples. So we developed an online risk-based authentication scheme that integrates mouse dynamics and free text analysis using a Bayesian network model. Of course, later on, we integrated both the mouse and keystroke dynamics together. So due to the limited amount of mouse actions or keystroke dynamics involved in a typical web session, relatively lower performance is achieved when using each of them individually. If you merge them by combining the two modalities, the overall performance has been enhanced significantly, as I will show you shortly. The performance metrics, false acceptance rate, false rejection rate, and also equal error rate when FAR equals FRR. The experiment evaluation of the scheme multimodal framework, we use 24 participants, and we get an equal error rate of 8.21%, which is excellent given the situation there. And these users, they were from all over the world. Actually, we have people from North America, Europe, and Asia. So as we mentioned, we consider in our work 2 different biometric modality, mouse and keystroke dynamics. We extracted a separate model of the user behavior for each of the individual modality using a Bayesian network. And to enroll a user, we extract for each separate modality a specific Bayesian network model from the enrollment. The extracted Bayesian network structure is stored as part of the user profile. So each user will have different Bayesian structure. To authenticate a user, we apply the monitored sample to the Bayesian network structure that correspond to the profile for the claimed ID. Keystroke dynamics here are divided into 4 categories based on the character ASCII code and on the mechanical layout, uppercase, lowercase, control keystrokes, and other. Okay. This shows you uppercase keystroke, for example. Lowercase keystrokes allow printing lowercase letters on the computer screen. Characters from A to Z fall under this category. Control keystroke don't result in printing. Example of these include the tab, backspace, and the delete key. For each category of keystroke, we calculated the mean and standard deviation of a dwell, or the whole time, as well as the distribution of each type of keystroke within a sequence of keystrokes. And the second type of flight time is when only 1 key out of 2 belongs to the uppercase keystroke. These 2 types of means are represented as the mean of flight time for each type of user keystroke behavior, as shown in the table to come here. This shows you the factor, the acronym, the unit, number of features, description for each of them. For example, mean of dwell time. That is mean dwell time of a sequence of keystrokes. Go to this one, mean of dwell time per category. The mean of dwell time for each keystroke category in a sequence of keystroke, and so on. In case of mouse, here we have 360 degrees, and we divided the movement into 45 degrees apart. So the raw mouse data consists of a mouse movement coordinate, movement angle, the time to move the mouse from one location to the other, and the time of mouse click. The mouse movement direction can be divided into 8 areas of 45 degrees each, as shown in the figure here. Mouse features are extracted from batches of consecutive mouse action, and by default, we consider batch of size n equal 30. We extracted 66 features from raw data organized under the 10 factors listed in the table we showed you earlier. The number 66 come from the combination of features. We have 8 direction-based factors, and each factor consists of 8 features based on the 8 movement, each of them 45 degrees. So you get 8 times 8, 64. And we have 2 statistical factors, mean and standard deviation. That's why we get in total 66. Each factor is actually a small feature vector. For instance, the factor pair mad underscore mad, that corresponds to the percentage of mouse action occurrences over a sequence of mouse actions in each mouse move direction. Since we define 8 direction, each correspond to 45 degrees. This gives us 8 features in pair_MAD, which is, as I said earlier, percentage of mouse action occurrences over a sequence of mouse action in each mouse move direction. This shows the mouse dynamics biometric parameters. This is the factor, average click, we call it ACT, and in seconds. And here the description, average of mouse click in time, and so on for the others. In table 3, it shows you the parameters there, the factors such as pair_MAD and so on. These are calculated for each of the 8 movement directions, 45 degrees each. As a result, each of these factors is represented by 8 feature values, each corresponds to a separate direction. A silence occurrence is identified when the mouse move is 0. The percentage of silence occurrences in a sequence of mouse action is represented by a feature silence ratio. Flight time is defined as the time between 2 consecutive keystroke in keystroke dynamics. First, the flight time value must be positive since the keys are pressed consecutively. Second, by analyzing the sample collected raw data for 5 random users, we observed that only a small amount of samples involve flight time beyond 3 seconds, which means we could filter out and save time. So based on that observation, the percentage of records with a flight time greater than 3 seconds is 5.34% in the corresponding keystroke sample. As a result, we applied a filter to remove data that's outside the range 0 and 3 seconds. For mouse, we apply 2 types of filter. First, we apply the moving average filter on the captured mouse move position data and computer screen XY coordinate and remove noise data on mouse dynamics feature there. Using the moving average, we take the means of 5 points as the new value of the center point. We apply the moving average filter on X coordinate and Y. The second filter applied on mouse dynamic is similar to filter applied to keystroke dynamics. In mouse dynamic, data set were collected for the above sample user. We observed the percentage of data with mouse move time less than 1.5 seconds and mouse move speed less than 5,000 pixels per second to be 97.44. What that means, therefore, we decided to filter out as noise mouse move time and mouse move speed failing out of the range 0 and 1.5 second and 0 and 5,000 pixels per second respectively for these 2 cases. That saves us the computation and time and give us outcome fast. We learn a Bayesian network to build the user profile and then use it to classify the monitor samples. And here, it is assumed that variables are discrete and finite. Since most of the features extracted from keystroke and mouse are continuous, we convert them into nominal feature through data discretization. The raw data consists, in the case of mouse movement coordinate, movement angle, time to move the mouse from one location to the other, and time of mouse click. And as I said, we have 8 directions, 45 degrees apart, as I showed you there. We have 66 mouse features. Examples are there, and I mentioned them earlier. We created a user profile at enrollment by training a separate Bayesian network model for each modality, for each user, whether it's keystroke dynamics or mouse. Example on these for 2 different users is shown here for different values of these parameters, which we defined earlier. Data collection and simple, we use social network collection data. Involved 24 participants for about 8 weeks. In total, we have 193 legitimate visits and 101 intrusive visits were contributed to the experiments. Again, 24 users with different backgrounds, different geographical region, and different computer skills. The experiment lasted for 8 weeks. So on total, as I said earlier, we have 193 legitimate visits and 101 intrusive. The table below shows the results there. mean number of samples per user and total number of samples per user. Whether it's keystroke or mouse gesture, there is genuine data and intrusive data. Only genuine records were used in the training. Genuine data is divided into enrollment and test based on the timeline. The earliest data received in time was used for enrollment, while the data collected subsequently were used for testing. For each of the legal users, the positive records in the training set considered of genuine enrollment sample for that user, while the negative training records consist of enrollment data from other randomly selected legal user. The number of selected users for training per user varied for each modality. The number of selected legal users for keystroke was 8, while the other for the mouse was 4. We use a stratified tenfold cross-validation to train the Bayesian network corresponding to a user profile. And in general, cross-validation is a way to predict the fit of the model to a hypothetical validation set when an explicit validation is not available. We then obtained the correctly classified records for the 10 tests. The correctly classified records are the record whose predicted class probability is over 50%. The percentage of correctly classified record, PCCR we call them, is the total number of correctly classified records divided by the total number of records. This table shows you the Bayesian network training records and validation results for different users, the positive training, negative training, and PCCR rate. Figure 2 shows the training there. And for users 2 and 7. In the verification stage, we apply sample keystroke dynamic record on the Bayesian network profile for a given user to compute the probability that the records were generated by the user. So this shows keystroke Bayesian network for 2 different users. This is for user 2 and 7, the bottom is 7. Keystrokes and mouse action were collected from a total of 24 test users. Due to limited number of sessions contributed by some test users, the total number of users having enough data for enrollment was 12. Averaging users' false rejection rate and false acceptance rate gave us the overall false rejection rate and false acceptance rate for that modality. The figure shows next here. It shows you the receiver operating characteristic curve, and when false acceptance rate and false rejection rate, when they are equal, okay, that's equal error rate. It was about 20 something, actually 24 or 22%, 22.4%. For the keystroke, for the mouse gesture, for the mouse gesture was 22.41%, while for keystroke it was 24%. So this shows it for the keystroke, it's about 24% here. If you go more for the mouse gesture, it is less, about 22%. When we combine the two, the mouse and the keystroke data, and integrate them, and we get an equal error rate of 8.2% when you combine them. And this is how it shows. This is the false rejection rate, false acceptance rate, and we get here when both of them are equal, 8.21%. To conclude, we introduce here a new risk-based authentication system for web environment that combines mouse and keystroke dynamics using Bayesian network models. Web environments are characterized by the limited amount of keystrokes and mouse gestures actions involved in many sessions, which makes detection hard, especially for a free sample produced without any predicted baseline. The proposed scheme provides us with an equal error rate of 8.21%, which is encouraging results. Risk-based authentication can be applied from 2 different perspectives, proactive or reactive, and each of them suits a specific application. When applied proactively. Risk-based authentication can be integrated with the login process and used to block from the beginning access to user flagged as risky. This is good for cases such as national security domain. In contrast, reactive risk-based authentication systems can be used to identify and revert ongoing or completed transactions considered as risky, such as in banks. Online banking. In other words, more stringent accuracy requirement underlie proactive approaches compared to reactive. As a matter of fact, each category is adequate for a specific application, while proactive risk-based authentication is important in situations where confidentiality is essential, such as military and national security transaction. Reactive risk-based authentication may be enough in situations where integrity is the prime concern. For instance, in online banking, malicious transaction, illegal transfers, and so on can be reverted immediately by the end of the session if the user is classified as risky. As shown above, the experimental evaluation of our proposed scheme provides us with an equal rate, which means forced acceptance rate and forced rejection rate equal 8.21%. Although such performance is not very impressive for a proactive risk-based authentication, we believe that it's good, adequate for reactive risk-based authentication. In this case, the goal is not to prevent the user from using the system, but rather to identify malicious sessions and trigger appropriate risk mitigation measures. In the future, we plan to focus on improving the performance of our proposed scheme by studying alternative machine learning techniques such as neural network, deep learning, and artificial immune system. We will also expand our experiment data set by involving more participants. And thank you, and I will be glad to entertain with your questions. Do you hear me? Hello?
Hello, Prashant.
Hello. Thank you so much,
Hello.
sir. Yeah, Prashant?
Yes, ma'am. Ma'am, I'm here.
Yeah, please carry on.
Okay. It was quite an energetic and lively session, sir. Thank you very much, sir, for your words. Yeah, sir, for your words of wisdom and familiarizing all our participants about the biometric-based cybersecurity with the help of many real-life experiences and examples. We are very grateful for the time and efforts you took to share your thoughts and experiences with our participants. Now, I would like to call Dr. Karan Singh, sir, to deliver vote of thanks to our speaker. Karan, sir?
Hello.
Yes, sir.
Yeah. So thank you, Prashant, and I welcome and thank you, Professor MS Obed. He gave so wonderful talk, and I think the authors, participants get benefited. And in future also, we will invite you in such type of the event, and we hope you will come and accept our offer. Thank you very much, sir.
Thank you. It's my great pleasure to be part of this outstanding conference. Thank you.
Should we take the 5 minutes break, sir?
Oh, Prashant.
Yes, sir.
Sir is there. You just start next speak. Okay.
Okay.
Yeah, just I am sharing.
Okay, sir. Good afternoon, everyone. I, Prashant Kumar, once again welcome you all for the second keynote speech of Online International Conference on Networks and Cryptology. We are ready for our next session to begin, and for that, we are very lucky to have Professor Bimal Kumar Roy, sir, from ISI Kolkata, joined as the speaker. Welcome, sir. I would be delighted to give a brief introduction of our speaker.
Yeah. Hello, Prashant.
Yes, sir. So, Professor Bimal Kumar Rai, sir, is the head of RC Post Center for Cryptology and Security in Indian Statistical Institute. He was awarded Padma Shri Award in 2015 and Teachers Award, Indian National Science Academy 2014. He has also supervised 13 PhD theses in four different technical areas, 3 in statistics, 7 in computer science, 1 in mathematics, and 2 in statistical applications. His primary research interest involves all aspects of statistics and its applications. Currently, he is working on combinatorics and application of statistics in cryptology and design of experiments. So I consider it a great honor to welcome Professor Vimal Kumar Roy, sir, who is going to give keynote speech on data obfuscation or secret sharing. I request you, sir, to please proceed over the session. Over to you, sir.
Okay. Thank you, Prashant.
Thank you, sir. Welcome.
Yeah, thank you, Karan. Since I'm kind of running short of time, I have another commitment. I forgot actually at one point at 1:15. What is happening? Okay, so I'll probably be very brief, and I'm very sorry that I can only speak for about 20 minutes or so. So what I'll do, I'll try to give an idea of this topic. Am I audible, Prashant?
Yes, sir. You are audible, sir.
Okay. So what is this problem of data obfuscation and why this is very important in the cyber domain? So I basically start with an example, and that sets the idea of what this subject all about. Now, we have sometimes very sensitive data. In fact, I can give first an example. What is this? Can you see me?
Yes, sir. We are able to see you. Sir, is there any PPT over there?
No. I have no PPT. I have no PPT.
Okay,
so
okay.
I'll just probably talk. So I'll probably introduce these two problems and why they're important and what is the current state of affairs in these problems.
Okay.
So I'll talk about 10 minutes on obfuscation, 10 minutes on secret sharing. So there are private information which people don't want to give away. This is very important. In fact, I'm actually in the government right now, and I'm in favor of publishing all information held by the government in a public domain. But naturally, then comes the notion of privacy. So what do I see? I certainly don't like it to get in a public domain that if I'm a defaulter of a bank loan, that my name is displayed there. There's something I don't like it to be in a public domain. So what you do, but I may not mind putting this data in a certain other fashion so that my privacy is preserved, but yet the information is there. So now initially people thought just dropping the names and identity is good enough. But I'll give you an example where this is not really good enough. Suppose we are talking about the loan defaulters or the loan takers by a bank. And in the address, we have got some PIN codes. And we need to keep the PIN codes because we want to also study the performance of the bank, whether they are giving to all areas equally or not. So we may drop the name and my identity, but the PIN code can be dropped. But suppose in one PIN code area, there is only one or 2%. Just 1 minute. So if you know that I am from this area and I took a loan from India, and then people can understand this is me. So this low frequency in a region could be adverse to my privacy. So there are problems in this way. So I'll just talk about one example by which I can actually impress you upon what we actually mean by the whole problem. Now I'm having some trouble with my this communication, this net here. And you have to excuse me. So sometime back, I was trying to get an idea of how many of my students do take alcohol. Now, this is a very private question, and if I ask the question straightforward to the students, they will not like it. So I designed a game. I said, okay, I know it's a very, very private question, and you may not like it, answer. So, but I propose a game with you, and let's play the game with. And if you see, if you can play the game very fairly with me. Okay, number one, I put two questions. My first question is, do you drink alcohol? Answer is yes or no. So you may put just capital A and capital N. And the second question is, are you born between January 1 and June 30? Okay, even the answer is yes or no. And the second question looks so naive, so stupid, but you would see that is my entire strength of this entire game. And then I ask you, toss a coin, and if it is head, then you answer first question, and if it is tail, you answer second question. And don't tell anybody what is the outcome of your toss. And then you write that Y or N in capital, just one letter. Put it on my table or in my office, put it in some box or whatever you want to put. So at the end of this game, what do I get? I get a bunch of slips written capital O, capital N on it. Now my first question is for the students that do you think from this information of a bunch of capital O and capital N, can I guess by any means whether a particular student is drinking alcohol or not? So the students are thinking, and they come to a conclusion like this, that see, from this one single capital letter Y or N, it's very difficult to understand whose handwriting it is. Even a top handwriting expert will not understand it. So from the capital letter Y or N, it's almost impossible for me to guess who has written that. But again, so your identity is somewhat preserved. And if by some magic I can guess that this is the handwriting of, say, Karan or Prashant or Indivar, know which question you have answered. Okay, so say Y or N, I don't know which question you answered. So your answer is actually kept secret or secured, and by that, and your identity is also not disclosed. So I'm obtaining two criteria. The identity is not disclosed, and also the answer is not disclosed. Okay, the content and the identity. So this is the essence of my data obfuscation. I'll put data in I'll transform the data in such a way that the identity is not disclosed, also the values are not disclosed either. So both way, I would be secured. Now, how do I achieve that, and why do I do that? So we may not mind people to compute certain properties of this information. Okay, so we have absolutely no problem. But the privacy is important, and this is often required by the community to know some picture about the government, the society, or even a school, the student body, whatever it may be, but without disclosing your identity. So what is the solution? So I told you a particular example which talks about your identity being preserved, and also your value is being preserved. So the way we put the problem is this. We have got some data points, say x1, x2, xn, and we don't want to disclose this x1, x2, xn. But we can define some functions of this x1, x2, xn. So we may define some 10, 20, or 100 functions of x1, x2, xn. So we want to compute the functions on this x1, x2, xn. But mind that x1, x2, xn are not going to be published on any domain. But what we can do we can transform this x's to y's. So I'll use a transformation. So each xi will be converted to a yi, and yi's are published or put onto a public web page, a public site with two properties. That from the value of yi, getting xi should be difficult. This kind of one-way-ness that you use in cryptography. And the other thing which is more important, which you normally don't have in this cryptographic domain, is that I can do any computation on this yi's. So I have to find out what computations I have to do on this yi's so that the function that I want to compute on x1, x2, xn can be actually computed. Okay, so in my example, I want to compute the percentage of my students taking alcohol. That's why I want to compute. And x1, x2, xn was the real responses. I didn't get the real responses. I got yi's. So after a toss, they played the game and they responded something, it's yi's. And I could do computation on the yi's. And from there, I could do this xi. Now I'll give the example. How do I do the computation on yi and then do the computation on x? So in my example, if I can go back, assume that there were 400 students and I got 136 yes. Then let me try to do certain computations. It's a little probabilistic game. So since this is head, I attempt question number 1, and for tail, I attempt question number 2. So roughly, if I assume that my coin is sort of unbiased, out of 400, 200 will answer first question and 200 will answer second question. The second question is extremely naive. Okay, and what is that question? Are you born between January 1 and June 30? So of that 200, we answered second question. Roughly half of them, so about 100 of them would answer yes. So I know out of my 136 yes, okay, then the other 36 didn't fall from heaven. The other 36 must be respond to the first question. Again, 200 of the students answered the first question. Okay, and 36 yes. So 18% of my students actually drink alcohol. Okay, so I do this computation on actual data by virtue of computing on the obfuscated data. So that transformation from x to y is called obfuscation. Now this obfuscation, I don't have a general panacea. So you can possibly have problem specific. So it all depends on the kind of data x1, x2, xn you have and the kind of functions you want to compute on. Accordingly, give a statistic of obfuscation. Now, this is a very important literature now because privacy is very important, as information is very important. So, if you have to give importance to both privacy and information, the only way we can make information public is through obfuscation. Now, one standard thing that we have used in our data is that it looks surprising to me. So, we thought we'll obfuscate with some observations randomly drawn from some probability distribution. So naturally, we try to use uniform distribution or the Gaussian distribution. And then you find that the computations become hard or not even possible. And we found out, actually very surprisingly, there's another distribution in statistics called Laplace distribution. And if we obfuscate the data from random observations from a Laplace distribution, we find it that this is very useful and we can gainfully obfuscate one-way-ness. And also we can do lots of computation on the actual data on the basis of the obfuscated data. Now, this is a very important area of research these days, and there are plenty of reference on this one. Somebody may say anonymization, somebody may say obfuscation, somebody may say privacy preserving computation, but all of these are pretty similar thing. And this is, I think, one of my and also one of the international community's current area of research in the cryptographic domain. So this is my problem number 1. And problem number 2, I wanted to highlight the notion of secret sharing. And as a policy, I feel unless this is a very personal communication. If you are dealing with a government or a body or an office or a college or institute, we don't want to encourage holding information, private ones, by only one person. So we want to define a group of people who will have the eligibility to retrieve the information, and unless they come together, you cannot get the information. An individual is not permitted, or maybe another group of people are not permitted to access information. The simplest example I'll give, we have these bank lockers. Now in the bank lockers, the bank has a key, I have a key. Okay, and with my key, I cannot open the locker. Even the bank manager with his key or her key, he or she cannot open the locker either. But when you put both the keys together, then the locker opens. So this is what we call the notion of secret sharing. Okay, but then I have some serious concerns, serious questions. I asked my bank, that number one, that these are mechanical objects, mechanical keys. Now I asked my bank manager, is there a proof that my key cannot be reconstructed? And the manager has no answer. In fact, when I was a student studying in a hostel, I used to lose my key all the time, and I'll just get a locksmith from outside the campus. He will come with some pudding. He'll put the pudding on the lock and get an impression of the inside. Okay, and then he'll just get me a key in no time at all. Okay, so this was so my first question was that my key cannot be reconstructed. And my second question was even more important, and that floored the manager. I told, what you have shown that with my key and your key, this pair of key, you can actually open the locker. But but can you give me a proof that there do not exist another pair of key which can open the locker also? So there could be another 1 million pairs of keys which can open the locker. All you have demonstrated, one pair can open. And I want to make sure that no other pair can actually open this locker. And he gets floored. So these are the issues in my, these are my issues in the secret sharing problem. So in general, what we do, we define participants. We have a secret. We have a number of participants, and we define the participants. Only this group people are eligible to access the secret, and no other.
Sir, I think ready with this.
Okay, and beside so it could be an example like that. We have a principal in the college, and all the student files which are confidential may be accessed by the principal and any two of the deans, because maybe the principal and the respective dean of the faculty. And we have to build a scheme how to access the secret. But then the tough part becomes to make sure that except this defined group of people who have the right to access the secret, no other group, no other subset can access this one. So this is where it becomes the difficult part, and we have to give a notion of what we mean by this these two concepts. They can and the others cannot. So I don't really have time to elaborate on that. So we take the help of Shannon's information theory, And we try to define Shannon's information in this context. We take the conditional entropy. So conditional on a group of participants with their shares of secret, the information will remain the same. Okay, but if I take any other number of participants other than my qualified set redefined, the conditional entropy is going to be zero. It should no information. So we have to make again a kind of probability model of how to share the secrets and make sure that these notions are satisfied. Now this is also very important, challenging task, and people are working on this area for quite some time, and it's very relevant. So I'll probably stop here because of my paucity of time. I have another thing at 1:15, so I'm already getting delayed. So if, I'm very sorry that I have to terminate to complete my talk in such a hurry. But I thought I could, introduce you to very important modern concepts, and why that event. And if you're interested, you can get in touch with me. We have a lot of work on this. We can communicate, and Karan can pass my email address to everybody, and we can communicate, and I can pass exactly what our contributions have been in this area.
Sure,
Okay,
sir.
thank you.
Thank you, sir. Thank you very much, sir, for such a nice session. I cannot applause just by sitting here, but I cannot stop myself by appreciating for giving such a wonderful keynote speech. Thank you very much, sir, for sharing the knowledgeable content with us. I hope that everyone is enjoying the same. Thank you so much, sir. Now, I would like to call
Okay,
Dr.
bye.
Karan. Now,
Bye.
I would like to call Dr. Karan Singh, sir, to deliver vote of thanks to our speaker. Karan, sir?
আমি উঠে গেলে ডিসকানেক্ট করে অন্যটা দুটো বাজে আসবে।
Hello, sir.
Hello, Prashant.
Yes, sir.
Hello.
Yes, sir.
Yeah, thank you. And we thank you to our keynote speaker, Professor Bimal Roy. And already he come and provide such type of the opportunity. And due to some reason the session was delay, so we applied for that. And we hope in future also we invite you, sir.
Sure. Anytime. And hopefully things will get better, and we can meet physically. Okay.
Yes, thank you very much, sir.
Okay, I'm really sorry for cutting short my talk because I have something else to do. Sorry. Okay. Thank you, Karan.
Yes, welcome, sir. Thank you very much, sir.
Sir, now we are heading for a 1 hour break. After that, I request all the participants to join our next session.
साक्षी, ये रिकॉर्डिंग चल रही है इस पे। Sakshi is there?
Sir, she's here, but I think not online.
आप अनाउंस करिए उसको।
Okay, sir. So we can take the break, sir. Now.
No, there is a break up to 3 o'clock, but for authors, the session will be start at 3 o'clock, and there are some paper ID. You just announce those paper ID which will be present. Okay, today's
Okay,
session.
sir.
So you will assign, announce, or I will assign announce. So there is a paper ID 1, then paper ID 2, paper ID 3, then paper ID 30. So this is the for session 1, and they are the paper ID 6, 7, 8, 9. These are the for session 2. Okay. So hope all author will come at the time, and because there is a time limitation already, you have seen if we delay in any paper, so everything will be delayed. So you just bind up your paper presentation within time limit. So already we have given the 15 minutes to each author, and you try to conclude your presentation within that time, including question and answer. Okay. So now we will close this session. If there is any query, we have already created one WhatsApp group. So we will respond regarding your query if you have anything in your mind. And if you need any support, then we will provide. So most welcome to all authors. And you just enjoy and you just learn something in these coming 3 days. Okay. So thank you very much. Okay, Prashant.
Okay, sir.
Yeah, we will join again at 3 o'clock,
Okay.
2:50 about.
Okay, sir.